Hello, I will start now. So, paper 2 and paper 1B. Okay, paper 2 and paper 1B. So now, please let me know which questions you want me to go through. Yeah, cause otherwise, I also not sure which ones you want me to go through. Iru, I got a clean copy here. So please let me know which ones you want me to go through. Then I explain. Okay, hang on. I tell you what. Can you type it in the chat for me so that yeah. Question 3. Hey, those Jethro, Ryan, Chaco, and Ephraim. I'm not sure what is your actual differences in the questions. Is it the same so far? Chaco? Yeah. So Laura is asking for 3 and 5. Did the teachers go through the paper already? Not yet. Are they planning to go through? Okay. Jethro is asking for question 2. So we got 2, 3, 5, 10. 2, 3, 5, 10. Question 2. Any part in particular or you... Okay, so question 2 looks like it's a HL question. Right? Yeah, it looks like a HL question. Question 2, 3, 5, 6, 7. Question 10. All right, so I'll just start out. You'll just type in, okay? Right. If you all have anything that you're not sure of, for Chaco and Ephraim, can I ask you to kind of like scan it to me or something? I'm not too sure. Yeah, cause then I can. Yeah, I suppose like if it's I'm not sure whether you're aware of which one is similar to this or not similar to this. Yeah, yeah, but I mean I'll go through question 2 for the rest of them first. Okay. Um, Jethro, are you there? Nope, he just logged off. He asked the question, he left. Oh, I'll wait for him. Or anyone else asking for question 2? Can I have a sound off or anything like that? No? Okay, I have to go on. I have to start. Maybe we will circle back to this, I guess, in a while. I'm not too sure where he is. All right, question 3. Okay, Laura? Yes? Yeah? What's the actual question you're asking for here? Okay, so Jethro, I'm going through this now because like yeah. Don't worry. But let me just go through this with Laura first. Part A3 is it? Is this one? Okay. So you're supposed to calculate the angle of the deflected electron, right? Okay. Uh, you're supposed to find this angle here, right? This is a bit weird. I mean, to me, it's like kind of like. Laura, is the momentum of the photon, the vertical momentum of the photon, is that not equals to the vertical momentum of the electron? Laura? Oh, okay. So, but I mean, it's like, okay, so yeah, it is the same because this is like a normal kind of collision, but in 2 dimensions. So you have a photon that has momentum and it's flying over here, it's colliding with the stationary electron here, and then it goes off like that, right? What's the initial vertical momentum of the system? What's the initial vertical momentum of the system, Laura? Yeah, 0, right? So by creating this vertical momentum here and this momentum here, right? The momentum of the photon here and the momentum of this photon here, they should net off. Yeah. Okay. But it looks like they gave us the initial momentum here, which makes me a bit worried because it feels like it's going to be very, very convoluted. That one question there is going to be like a lot of work. So I'll try to do whatever we can. So we understand that this is the vertical and this is the vertical first, right? Technically speaking, could you find the vertical component of this momentum? You can, right? You can find the vertical momentum component, right? Which is what? Cosine? No, I sine lah. What cosine? What? So you go and find out what's the momentum of this guy first, which is what? Lambda. I mean lambda equals h over p, so p equals to h over lambda, right? P equals to h over lambda. Like this will be the total momentum at this angle, and then now you have to find the vertical component of it. So how much is this first though? Can you like work it out and punch it in and tell me now? We're doing a paper review, guys, so you know. Oh, whoops. Sorry about it. Shit. Some of my old. Okay. Wait a minute, I don't get it. There we go. Yeah. Did you find this one already? How much is this? Okay, 6.63 times 10 to the power minus 34, right? Divided by 966.8 times 10 to the power minus 12 meters. Okay. Let's do this. 6.63 times 10 to the power minus 34, then divided by 966.8 times 10 to the power of minus 12. Right. So I get a momentum of 6.858 times 10 to the power of minus 25, right? And what we need to do is we need to find this component. So this component here is sine 75. So 6.858 times 10 to the power of minus 25, right? And then sine 75 degrees. Right, do you see that? Does it work for you? Okay. So what turns out is that the momentum, the vertical momentum of this electron, right, must be the same value as well, but you know it's just pointing the other direction, right? So it's this one here as well. Okay. I guess in a way the problem now would be, right? We got the vertical component. Now we need to find the horizontal component in order to find the angle, because we can use like trigo, right? We can use trigo, horizontal, vertical, tangent, alpha. We can use alpha that way. Did we not find anything about the electron before? I haven't looked at the entire paper yet, so show that the momentum of the deflected electron. Oh, hang on. Oh, we have this. Oh, okay. So very clear. Actually, very well. We already have this. The momentum of the deflected electron is this. We already got this, right? So 8.35 times 10 to the power minus 25, which means that this way is 8.35 times 10 to the power minus 25. Okay. So knowing that the vertical component of this photon must be the same as the vertical component of the electron, we can now declare that, right, the 6.858 times 10 to the power of minus 25 times sine 75 degrees, right, is equals to 8.35 times 10 to the power of minus 25 times sine alpha. Yeah. Does it help? Right? I mean, I'm showing you the working, but you know, I hope you understand what's going on here, yeah? So this will be, I don't know her working here. I'm not too sure what her working is. Oh geez, it looks like she might have gone a long way around this. Man, I'm a bit concerned about this. Is this part 3 a different scenario or is it the same scenario? Because they are giving me the momentum of the photon here, but they're also giving me the wavelength of the photon here, which is kind of like, I hope it's the same. Am I supposed to assume it's the same? Or did they give me a different scenario here? No. She went to accidentally calculate the same wavelength, 9.65 times 10 to the power minus 10. Yeah, come on, man. So I think she went a long way around this, right? So there was no need to do all this. You can just use the vertical component to yeah. So I'm just like wondering why the teacher gave the tick here. There was no need for this. Okay. Is there another part? Sorry, what? But I thought she just calculated this and it's the same. No. It's the same. This is 965 times 10 to the power of minus 12. This one is 9.65 times 10 to the power minus 10. Yeah, it's the same. So it's a no need. What she did this to prove that it's correct. I guess, right? You know, she probably did this to prove that it was the right value, which it is the right value. But all these are all unnecessary. So all you have to do is really just to compare the vertical components here and here. Laura, is there anything else from question 3? Is there anything here? Part B, this one? Okay. This exact question here? This one? Okay. The one below as well? Okay. So during beta decay, right, a beta particle is emitted, right? Are beta particles easily detected? No, they are actually. Yeah, they're easily detected. I mean, beta particle is a negative charge. You put a Geiger counter, you can detect it. It's easily detected. You get what I'm saying? Right. The idea here, what they're trying to say is that we have a parent nuclei, and the parent nuclei decays, and when it decays, right, when it decays, the daughter nuclei goes this way, and the beta particle goes this way. Correct? If beta particles was the only particle that was emitted during a beta decay, would it go this way at an angle? Why not? Mm-hmm. Based on what? Yeah, based on principle of conservation of momentum, right? If beta particle, you can answer it in a negative way. You can say like, if the beta particle was the only particle from a beta decay, then the beta particle should have been ejected or emitted in the directly opposite direction of the daughter nuclei, right? Because based on conservation momentum, right, the momentum of the beta particle must be directly opposite of the daughter nuclei, so that the total momentum of the system is still what? Is still zero. Okay. Hence, for the beta particle to have been emitted or ejected with an angle away from the line of direction of the daughter nuclei, it means that there must have been another particle that was emitted, right? Another particle that was emitted together with it, which happens to be the. What particle is that? Oh no, it's a neutrino. Yes, yes, it's a neutrino. In fact, if it's a beta plus particle, it's an anti-neutrino. But yeah. Okay, so but the problem is you gotta remember that neutrinos are super hard to detect, which means that in any given lab environment, right, there ain't no way for us to detect the neutrino coming out of the decay. It's like there's nothing that we cannot put a GM counter or anything to detect. There's no detector to tell us that, oh, that's the angle that's coming out from. At higher level experiments, they try to use bubble chambers, right? Neutrinos just pass through the bubble chamber. It's not going to create a path anyway, right? So that's the problem with this. This one also, right? Determine x to y after a time of 4.5 half lives. Is it 4.5 half lives? Correct. Yeah, that's a math question. That's a primary school math. Oh no, what's your mistake? So x decays into y, right? X becomes y. X becomes y. So you're looking for the ratio of, yeah, okay, like whatever she wrote is absolutely right. You're looking for the ratio of n over n naught minus n, like this. Yeah. So you know what? You can assume a number. You can assume number 4.5 half lives. That means like n is equals to n naught, like half to the power of 4.5. Yeah. Okay. And then you put this on top, and you do this one. You do the math. You should be able to get something like this, I suppose. Yeah. Where do you go wrong? Where do you go wrong? Okay, yeah, that's not good. N over n naught will be just simply the ratio of y to x. Like n, no, sorry, n over n naught will be the remaining x versus the original number of x. It will be like n over n naught will be like n naught minus y over n naught. Like that's what's happening there. Yeah. Okay, that's fine. Back to question 2, Jethro. I'll do Jethro and then I'll come back to Ephraim. Ephraim, you sent me a question I just saw, so let me come back to Jethro first. Jethro, what's the thing that you're having trouble with here? Part C. Okay, so this gravitational potential at the surface of the sun, all right? Mass of Earth, distance of Earth to sun, radius of sun, right? Outline why is negative. I think we've gone through this before. There are 3 reasons why they give 2 marks, but we usually just write 3 reasons. Let me just check. Okay, that's fine. Okay, that's fine. Gravitational potential energy of Earth in orbit around the sun. Give your answer to appropriate number of significant figures. Well, what's wrong with this, man? Jethro, are you asking for this question? Like, what's the issue that you're facing, or what do you do wrong, or like what were you trying to do? Work done formula instead of minus GMM over R, isn't the same thing? Oh, oh man. Okay, okay. So you got to understand the context. The context is the sun is like this here, and then the Earth is orbiting around it, right? So the Earth is going around it in an orbit like this. Okay. Basically, the question is asking like at that distance, at this distance, right? At this distance, what is the GPE of Earth? Right? What's the GPE of Earth with respect to the sun? So the Earth didn't start from the surface of the sun and moved all the way to this position here, right? The Earth has always been like this far away from the sun, right? So the GPE would be negative G big M small m over R. Yeah. Okay. Right. So yeah. Specifically, if you follow the lessons I taught in D1, I did mention that when you use this equation, you're basically finding the spot value. Like, what's the spot value of the GPE? Sometimes they want you to find the spot value, which is in this case, right? They want you to find the spot value, right? Spot value. That means the value at this distance R. Sometimes they want you to find the change. Like, how much change does it take to go from, like, one point to another point? You get what I'm saying? Yeah. Okay, that's no worries. This one, no issues? Actually, come think of it, what's wrong with this question? Like it's a bit suspiciously a bit too easy. Let me just double check. GMM over R. Oh, they didn't give the mass of the. Oh yeah, they didn't give the mass of the sun. They gave the potential on the surface. So it's not so easy. It's not so easy, right? They gave the potential here only here, right? They give the potential here. They give the potential value here, which is given as 1.9 negative 1.9 times 10 to the power 11, right? So negative 1.9 times 10 to the power 11. Okay, all right. They want you to find the spot value of the GPE here, which technically means you're finding GPE is equals to negative of V times M, right? V times M, right? But the potential must be at this distance, right? You need to find out what's the potential here, like V is equal to how much here. Then if you can find the V, you can multiply to the mass of Earth, which is given, right? The mass of Earth is given here. So that's the tough part lah. The tough part is understanding how to find the potential at this distance here. Do you understand what's the trick of this question now, Jethro? Okay. Yeah. Right. So this potential is for the radius, right? So you can write like negative 1.9 times 10 to the power 11 over the radius of the sun, and that's equals to the potential here, like V at R, right? I'm going to write V at R divided by the distance R, okay? And in fact, R and R are given. Radius of the sun is given. Radius of the sun is given here. Radius of the sun is given here. Distance from the center of the sun to center of the earth is also given here like this. So basically you use those two values to find VR. And then you take this VR, you multiply it to here, multiply it to the mass of the earth. This will give you the GPA of the earth. Okay, that's the tricky part to this question. Yeah. Anybody need me to clarify this? Let me know. Otherwise, I'm moving on. I'm moving on to Ephraim's question for a while. All right, calling once, calling twice. Sold. Okay. Let's look at your question, Ephraim and Chaco. Chaco. Okay. So what's this question? Sorry. Ephraim, Chaco. No. As in like what is the issue you're facing with here? Okay. Okay. That's fine. So basically, you have two wires in space. Am I right? You have two wires in space, as in like you have two wires like hanging out like somewhere around like here, like this. Correct? Two wires. And what we're doing is we are looking from the top view, right? We're looking from the top view, and the currents are going into the page. From our view is going into the page. Do you see that? right? So we're looking at it going to this page. So what they're asking for is there is a triangle that they want to like draw, or rather there's a triangle. So the triangle is somewhat like on this plane. You see that on this plane, and from the top view, that's how it looks like. So from the top view, it looks like this. Okay so far? Okay? Can All right, hang on They want to find out what is the magnetic field at Q due to wire X alone. So you're given a wire with a current and you're asked to find out what's the magnetic field at Q due to one of the wires alone. What that means is if I simplify it, if I simplify this concept here, right? Okay, if I simplify it, all I'm doing is I am trying to look at a wire here, and I'm asking for a random point on the side here like this, right? What is the magnetic field there? Right hand grip rule, thumb pointing in, you draw a magnetic field of a circle. Okay, so I draw a magnetic field of a circle like this. Well, let me just try to center it. Oh, it's quite centered. Okay, something like that. All right. So let me move this pointer. This point here. Let me move him. That is somewhere there like this. Okay. Right. Chaco, Ephraim, do you understand that the magnetic field is pointing at a tangent to the circle here? Right hand grip rule. Right hand grip rule. Like this. No, no, you don't. Basically, you're not supposed to draw the circle. I drew the circle just for you to see it. You're supposed to just draw the arrow. You understand? Oh, how do you know the arrow direction without drawing the circle? Okay. Is this 90 degrees? Is the triangle here 90 degrees here? It is, right? So basically, if you treat this like the radius of the circle, then the direction by X magnetic field is a tangent to the radius. Like that. Yeah. I mean, it's just so conveniently that they give you a right angle triangle. Yeah. But yeah. Then after that, for Y, right? You see, for Y, you look at this. For Y, if I do it the same for Y, okay, right hand grip rule, okay. The weird thing is that for for Y, the magnetic field points that way. Do you see that? At this point, X curls this way, so the magnetic field points this way. At this point, Y magnetic field curls this way, so the magnetic field points this way. So the resultant magnetic field points where? The resultant magnetic field points? No. What? No. You got one magnetic field pointing this way, another magnetic field pointing this way, right? Resultant is in the middle. Ephraim, you have an issue with resultant forces. Yes, you have to be aware of that because I sense what you're mistaken by, right? Because this is a very common secondary school problem, right? They draw like that, right? Then they think, oh, resultant force must close triangle. Absolutely wrong. Okay, right? It's not. So always think about this, right? Don't go with the triangle method. Don't think about like forming a triangle. Think about this. If someone pulls you this way and someone pulls you this way, where would you end up going? Through the middle. That's the resultant. Okay, Ephraim? Okay. They ask you to determine the magnitude of the resultant magnetic field at Q. The magnetic field at Q due to wire X alone is 15 MT, right? 15 milliteslas, right? It's I mean, we have to do it anyway. Okay? So, one other way, right, Ephraim, look at this, is you can move this up. You know that there's one going this way and there's one going this way, right? Okay? I can move this one, I can move this arrow, I can move it over to here. Okay, I can move it from here to here. Do you see that? I'm moving it without changing its angle. Do you see that? I moved it already, right? Then the resultant is here. This is the B net, the net magnetic field strength at Q. B net. All right. That's just like me moving this arrow over to here, and therefore the resultant is that red color arrow there, like this. I'm ask you this: if this is 15, right? If this is 15 milliteslas, and this is 15 milliteslas, and this is a right angle triangle, the resultant is, yeah, right, square root of 2 times 15 squared. We good? Yeah, cool. Right, that's the question here, lah. Okay. Back to the HL papers. SL, continue to look through your papers and let me know if you need anything. Laura, back to you. 5, is it? This one here? Yeah? Okay. Now, usually for these questions, I'm a bit afraid because IB sometimes want to treat this as a kind of like a standing wave. Sometimes they want to treat it as a two-source interference. But do you understand that it could be both? It could be either. Right? You could form a standing wave here. The sound travels over there, reflects backwards, and then you get standing wave. So the microphone could be at a node, anti-node, right? Or it could be that you can consider it to be a direct wave here, and then the wave goes over there, bounces back, and then it could be a constructive or destructive interference, right? Which is the same as node or anti-node. Okay? But, oh, they did say standing waves, right? So what are the 2 necessary conditions to be standing wave? Hey, what's this? All right. So standing wave must be traveling opposite directions. Same type, same wavelength, yes. Okay, same type, same wavelength, yes. All right. And then the wavelength of the wave must meet the boundary conditions of the instrument, right? Then you can get standing waves. Okay, so we'll like that's not good enough an answer. What are you looking for? Which one? Everything. But this one you need. Okay, so this one here, yeah, you see the word anti-nodes and nodes. Yeah. Okay. I mean, just I mean, if I mean, I'm gonna tell Anna to watch out for this one here. Okay, just be very careful of this. So what this student stated was that anti-node, highest amplitude means the loudest sound. Node means lowest amplitude means the lowest intensity sound. I get very like irked a bit. I'm getting a bit irked because first half of the sentence it says amplitude, second half of the sentence says intensity. Like, you know, just be consistent, stick to one thing, right? Okay. But I'll tell you also that it is not true where the anti-node, right, is a loud sound and the note is a soft sound. I mean, you can say anti-note of loudness, I suppose you can, right? So anyway, but yeah, this entire thing is you describing how a standing wave is formed, and why are there regions of loudness and softness, right? Because of the anti-notes and notes. Yeah. So I mean, this will be the standard answer. What did you write, Laura? Uh huh. Okay. And you got marked wrong. The whole thing 2 marks gone. Okay. Firstly, you have to state how it's formed. Okay. Right. How it's formed. And the thing is this: why did you write that? Why did you write the note is where the loud sound is and where the antinote is where the soft sound is? Is it because you remember I said that? No, but why would you say that the antinote is a soft sound? Antinotes are big amplitudes, you know. Okay? Low, you mean what? Soft sound? We're talking about sound wave here. You got to get rid of the idea. I mean, for the microwave, the melted chocolate parts are the antinodes because the amplitude of the standing waves are the highest there, right? Okay, okay. But I'll tell you this, okay, guys. Everyone, listen up, All right. So she writes antinodes and she writes that this one, the microphone hears a loud sound, right? This is not necessarily true, but I think the teacher gave it anyway because you could argue that this was the antinote of loudness and therefore it's a loud sound. And this is a note of loudness, which means it's a soft sound. This is fine, okay? Right? Just be aware that I actually did mention before for a sound standing wave, please do not make any correlation to antinodes and the loudness. All right. What you want to do is you want to write a more generic version, something like this. Right, when the standing wave is formed, your first mark is describing how the standing wave is formed. You must make sure that your incident wave is reflected, and then it superposes or interferes with the reflected wave, right? And therefore it gives rise to the standing wave, right? Then you just want to make sure that you say that the standing wave has nodes and anti-nodes, right? Where the microphone will pick up, high and low intensities, right? High and low intensities, and then leave it as that. Do not try to assign whether or not the anti-node or node is specifically whether it's a loud sound or soft sound, right? Notice how if this teacher marked it correctly, right? The correct way of marking, right? He marked it at the anti-node, meaning that the moment he saw anti-node, right, he already knew, all right, that's correct already, right? Then the rest of it, I think he probably like, it's okay, right? This student understands it. But Laura, whatever you wrote, you actually got 0 for it, right? You didn't get any marks for it, right? Possibly because, right, you are suggesting that anti-nodes have low intensity. But I want to make sure that you understand that anti-nodes have high amplitudes. Yeah, right. The air particles move with great amplitudes. Okay? And then I want you to remember not to correlate that to a loud or soft sound. Yeah. So generically just say like, there'll be regions of antinodes and nodes where the microphone will pick up, right, louds and soft sounds, right? And then just leave it as that, right? And then, the teacher will see it already, like the examiners will see it already, and then, all right, you get the idea. Okay? Right? Because there's actually a deeper understanding for this. In fact, whatever Anna wrote is not quite right, but I'm not going to tell you that because I'm not going to teach you that because that's going to be a lot more complicated. Right? It's about how the air particles move and all, right? So, yeah. Yeah. This thing here, you got it wrong as well? That one, okay? Now about the calculations here? Huh? The distance between two successive loud sound positions is 0.6. So that's between antinode and antinode. Antinode, that's half a wavelength. Do you put it as one wavelength? Huh? So 0.6, you put it as half wavelength? Then where do you get it wrong? Wait, do you not get 283 hertz? Oh my god. Oh no, NV over 4L is when you're trying to find harmonics. Like you're trying to find the harmonic. We're not trying to find the harmonic. We already got this information already. We already know what's one wavelength. Okay, this thing here, I'm gonna tell you this is the lack of practice, right? Cause whatever it sounds like you're still a little bit shaky about this thing here. Yeah, yeah, Ryan, you just sent me something. This one here. Now amplitude oscillation of the air particles, so it's negative. Yeah, because the particles are actually moving back and forth from its equilibrium position, right? Yeah. Now, dude, give me the definition of amplitude. Definition of amplitude, man. Definition of amplitude is the maximum displacement from equilibrium position, which means that it can be positive or negative, dude. Okay? Alright, cool. No problem. Yeah, I saw your picture. Ain't no way. Yeah. Okay, so that's for number 5. Let's look at this. Jethro is asking for 6. Right, what's up, Jethro? Which one? B1. Look at B1 here. Okay, B1. Okay. Is there anything at C? Is there anything at C, or is it just the midpoint? No, like I mean, there's a charge here. There's another 2 charges there and there, right? Is there anything placed here, or is it just some midpoint? Is that the point of equilibrium? Okay, okay. So this positive charge here, right? This positive charge here is going to experience a what? It's going to experience a net force, is it? Okay. And why though? Why would it experience a net force? By what? By the 2 big guys here, is it? Like what's the charge of this one here? Like is it positive charge or negative charge? Both positive. Both positive. Like positive volts means positive charge. Okay? So this is a positive charge and this one is a positive charge. Okay. What's the direction of force by the guy on the left acting on this small charge? What's the force acting on this guy? To the right. Okay, so I'll just draw a force to the right. How about the force by the right side on this charge? To the left, right? Notice how I drew the force by this one here pointing to the left a bit bigger than the one here. Why? Correct, that's right. Okay. So they tell us that the net force is given as this. So which means that this force, right? I mean, if I call this 1 and this is 2, right? Then this is F2 and this is F1, right? And then basically the net force F2 minus F1, okay? F2 minus F1, right? The difference of the force is this amount here, this one here, right? Or not? So explain why charge Q will execute simple harmonic oscillation about point C. When we are supposed to explain SHM, what's the 2 defining qualities of SHM? Mm-hmm. And acceleration is opposite direction. So what you need to do is to state that, right? Since the net force is equals to this, that means net force is directly proportional to X. Net force is F net equals to MA. Right? Means that acceleration is proportional to X. Okay? And then you have to say that when the positive charge is displaced to the right of C, it experiences a net force that's pointing to the left. Therefore, right, the charge experiences an opposite direction of acceleration to its displacement. Hence, it is SHM. No need. No, do whatever I just said. That's the answer. Like literally, that's all there is. SHM, to prove that it's SHM, what do we have to say? We have to say that acceleration is directly proportional to displacement. According to the equation, it is, and acceleration is opposite in direction of displacement, right? And we just say that when the charge is displaced to the right, the net force is pointing to the left. Therefore, it's opposite direction, and therefore it's SHM. Yeah. That's all you have to say. Don't need to go into any further detail. Don't have to say like as it goes to the left or goes to the right, then the force will point there or point this, right? Yeah. Okay. Matthew Chaco. What's your question? Chaco. Wait, I need. Yes, hang on. I need to. This one? Fixed mass of ideal gas has a volume of 0.012 meters cubed at a pressure of 5.4 times 10 to the power 5 pascals at a temperature of 57 degrees Celsius. Red flag there. Make sure you convert to Kelvins. Which is how much? Okay. Show that's approximately, you can do this. Gas in helium with molar mass, so this is average speed of this one. I think you can do this. Did you find the mass of a particle? Or one single particle? You didn't? Oh, you didn't? You just went to find the whole mass. You just went to find the total mass of everything. No, you got 0. Oh, geez. They're asking about this question. Ah, okay. Alright. Hey, Chaco, you owe me a drink, huh? Yeah, because I went through this many times already. You go and get my recordings for B1 and B1. Eh? Oh, I think the reason why you are not familiar with this is because I did go through this in B1, but I did this in B3. B3 also like fool. You fool. This is on you. Okay, but I'll go through it with you now, right? So you just have to make sure that you catch this. If you whatever I go through, you still don't understand, please make sure you go through in the video. All right. Helium with molar gas of 4 grams, right? Calculate the average speed of the molecule. Right? The equation that you should be looking at is E bar K equals to 3/2 kBT. Right? I think earlier today Cassandra was like very confused by this because like I think your school, like IB official question will say average speed, but then I think your school teaches this thing called RMS speed. Am I right? Have you heard of RMS speed before, Chaco? Yeah? Okay. Then she was asking me like what's the difference, right? And I tell you that according to the IB syllabus, it's the same. Right? It's the same. IB syllabus, when they ask you for average speed, they're literally asking you for RMS speed. But then some students like like not just her, like a couple of students before have gone on to like internet and then started searching like oh what's the difference between average speed and RMS speed. And in fact, on the internet there is a difference between average speed and RMS speed. That's the problem that we are facing here. It is calculated differently average speed and RMS speed inherently are different because of the way they are being processed. Is totally different, okay? But in this IB syllabus, which is very annoying, whenever they ask you for average speed, we take it that they're asking for RMS speed, which is basically just us finding V. Okay? So from this equation, okay, let me expand this equation, okay? This E bar K here is supposed to be half. Okay, the correct way of displaying it should be half C squared, like this. Half MC squared. Do you see that? Okay? This term here, this ugly looking thing, alien looking thing here, right, it's called mean square speed. In all cases, you're supposed to find root mean square speed, which means you're supposed to find this. Okay? Right, root mean square speed. But with the IB syllabus, I think they reckon that a lot of the students see this term and then like, oh my god, my eyes are going crazy. I cannot see anything here. Right? I cannot focus anymore. Like there's too many lines going on. You know what I mean? So we kind of like have to give them a bit of like help them out a bit, right? Like make it not so so complicated. So what IB did was that they just changed it to V. They just called it V. Right? V squared. Okay? And then they just said, if I'm asking for the average speed, you find this value here. Right? That's all they want. Okay? Because at the end of the day, when you're finding V, right? When you're finding V, that's the same as finding whatever we were finding just now. This complicated looking thing. But in math, right, read this thing as a combination. This is root. The triangle bracket is mean. Then the C here and the square here. Then the C is representing the speed. So if you go on the internet and you go and search this thing here, the root mean square speed, is a thing on its own. It's a special way of calculating like the speeds, right? Whereas this one here, this thing here is like an average speed, which is inherently different, right? They're different, okay? But IB just says, can we just simplify it? Let's not scare our students. Let's make it a bit simpler, right? Can we just put it as V? All right, let's just leave it as V, guys, please. All right, so that's what they did. All right, and basically you're supposed to find this. You see that? That's the answer here. However, so while T is what? T is very straightforward, 330 kelvins, right? Okay, what is M? So M, most students would think, oh, M what, right? 4 grams, right? Absolutely wrong, okay? M is 0.004 divided by 6.02 times 10 to the power of 23. I know you don't take chemistry, but you really have to remember this. Okay, so when we deal with this half mv squared, this m is the mass of one molecule. Okay, all right, then the next one is what? Density. There you got this wrong. How did you get this wrong? How did you get this wrong? Oh my god, I'm about to kill you. What's this? Oh no, wait. Why is it not ECF, man? Why is it not ECF, man? This one? Mass of one molecule? Okay. What do you understand about molar mass? 4 grams. What does it mean? Oh, 1 mole of helium is 4 grams. Okay. 1 mole of helium atoms, the total mass is 4 grams. So you take 4 grams and you divide it by the total number of particles in that 1 mole. That will give you the mass of each helium atom. Yeah, each particle. Yes, that's right. What's an alternative to this? You could write for you. You get the same answer. Yeah. Okay? But you have to be very careful about this because if they're gonna tell you that molar mass 4 grams, you're gonna put 4U, right? Some teachers will not be happy and they'll take away 1 mark from you. They just they just not happy on. Yeah. Midlife crisis. Okay, hey Chaco, what happened here, man? No, no, what are you saying sorry for? I don't get it. Like pressure is 5.4 times 10 to the power of 5, okay? Right? And then remember right, that you thought that V squared wasn't it like yeah. Did you write down the equation wrongly or anything like that? It's one third, right? It's one third, right? One third NM V squared, right? Yeah, one third NM V squared. Yeah. So why is there no ECF? Why didn't you all fight for it? Huh? Yeah, go tell him, man. Hey, dude. Sorry, what? Oh no! I'm sorry, Chaco. That's your answer there. Yeah, too lazy to give you the ECF. Oh man. Yes, Mansa. I don't know. Where do you get the density from, man? How do you calculate the density of helium? Oh, dude, no. This volume of ideal gas, 0.012 meter cube, is not 4 grams. So molar mass of 4 grams, right? Is like a oh. Wait, hang on. So you went to find the number of moles, then you went to multiply by the number of grams. Okay, talk to me, come. So what's the total mass that you got? So 7. You basically just took number of moles times 4 grams, right? Yeah. So what's the no lah? They should given you everything lah. No, you have to you have. I mean, no, I don't know, man. You have to tell them that you did. There's nothing wrong with what you did. You did it absolutely correctly. That's just the teacher's problem. Speed of the gas. No, you use this equation, right? You use this equation. Yeah, the density is the mass of the gas, man. It's totally fine, ah. Then divided by the total volume, right? You basically the total volume is 0.012, right? So you're basically using this equation to work out what V is, right? Yeah, you should have gotten the full marks, man, for this. Like there ain't no way, right? That makes no sense. Yeah. Because the next part is finding the density, right? Your density value would have been the same up here and down here, right? Yeah, it shouldn't be a case. No, in no way. It should be correct. Yeah. All the equations are just basically manipulations of each other. Like this density equation, right, is a manipulation of this equation here, you know? Yeah, yeah, that makes sense. Sorry, man. I'm sorry that you lost the mark, but in a way you should have gotten it. Yeah. Um What's the next question? What's the next question? What do we have? 7? 7C part 2, part 3? 7? Oh, what same thing? Okay, part 2, part 3. Okay, can. No problems. Ethan's asking for 10. Oh no, 7A. Okay, 7A. Jillian has 4C. Sorry, Jillian, did I catch your 4C? 4C. This one? Okay, so 71% of the Carnot efficiency and power produced is 1.33 gigawatts. What's the waste thermal energy released per hour? Well, it's a lot of work, man. Okay, so firstly, what's the Carnot's efficiency? Do we get it ready? It's this one, right? 29.7. Jillian, are you there? Is she still here? Jillian's gone. She texted me and then she's gone. Where did she go? Okay. Anyway, I'll record it for her. I think maybe she has something on. So this thing here. Right. So it's 71%. So 0.71. Right. 0.71 times what? 29.7. 29.7 efficiency. Right. And therefore this works out to be 0.71 times 29.7, right? And that works out to be 21.087% efficiency. Okay, right? So when they say that the power produced is 1.33 gigawatts, that's the useful power that's output by this plant, which means that this 1.33 gigawatts is the 21.087% of efficiency. You know, like this represents that. So the question now is, what's the total input of energy? Like now I need to find out what's the total input of energy, and therefore the total in, right? The total in will be equals to 1.33 gigawatts divided by 0.21087, right? So we'll go with that. 0.21, so 1.33 divided by answer. So the total in is 6.307. 6.307 gigawatts. Okay, gigawatts. But they ask you how much waste thermal energy is released per hour. So now we need to take 6.3077 gigawatts minus away the 1.33 because this is the useful output. So we take this, we minus that. That's the thermal energy. That's the thermal power, right? That's being lost to surroundings. So power loss will be equal to 6.307 minus 1.33, right, gigawatts, and therefore that works out to be 6.307 minus 1.33, right, and then we 4.977, right, so that's 4.977 gigawatts. Now then they throw us another last curveball and tell us that we have to find it per hour. My gosh, then this is per second, so we need to take this value times 10 to the power of giga is 9, right? And then multiply by 3,600 seconds in 1 hour. So energy loss, right, in 1 hour is equals to this value times, this value in gigawatts multiplied by 3,600 seconds, and therefore we get 1.79 times 10 to the power of 13 joules. Right, that will be the energy loss. Sorry, Jim, I don't know where you went. I'm recording this for you. I'll send you the recording later. But yeah, all right. I hope this helps you to understand this question. All right. I got I'm jumping over the place now. 7A, Jethro. 7A. Let's look at 7A, Jethro. 7A. What's this? What's this one here? Yeah. Don't know how to start from this one. Hang on, Let's see, Okay, so this one here is the works, basically the works. But you know what? This one I have done in B2 before. Okay, this one I have done with B2 before. Can I refer you to the video first before we come back to this again? Have you actually watched this one before, like me doing this thing here before, like B2? Ah, okay, can. Then you better catch it because it's a long run for this one. This one will take about like 20 minutes to explain. Um, yeah. I mean, I can just show you the working, right? Or I can just say, oh, you just remember this equation, that equation, this equation, but you won't understand it at all, right? So hang on, let me just see whether I can find it for you around here somewhere. So I was just doing this B2 with my year 5s. With your year 5, sorry. Something along these lines here, yeah, something like that. So like, we go through all of this, right? And then if you watch it on a recording, you can fast forward it and then becomes like, 10 minutes, right? Okay. So I did show how to use the luminosity equation to determine what's the power output of the sun, and then afterwards I go on and I lead on to the whole thing here. So the whole like, the whole works of how the equation ends up being, or the value ends up being like this thing here, like this, right? It's all written here. You know what? I'm just gonna send it out right now. Wait, oh wow, okay. So I mean, it's lengthy lah, right? Sorry, it's 45 minutes. But if you play it fast enough, and if you skip some parts, you should be able to get through it quite quickly. Let me just no worries. Okay, so let's do this. But the numbers are a bit off, right? I have different numbers, right? But I guess that's what it is. I will send it on the Telegram. Hang on. On the Telegram. Year 4, 2025. Oh my gosh. I'm running out of space already, man. Okay, hang on. I'll just put it on the general. I'll put it on the general. I'll attach a screenshot here. Wait, hang on. Attach a screenshot here. And then I'll attach a screenshot of the question there just for you to see how it goes. This one here. And I'll tag you to it. So I mean, it's not just calling you out. Oh, I can't tag anyone. So yeah. Okay, there we go. Right. So that's there we go. That's the one there. Right. So explanation of how it's done is there. Okay, good. It takes a while. It's very long, but then if you play it fast forward or like you just skip some parts. I think I took a break somewhere halfway, right? And then you can skip that part, so it should be a bit faster then. The next one is 8. 8A. Is it, Laura? 8A part 3. Determine the distance of data 1 Orionis in AU. Okay. Oh, data 1 and Orionis in AU. Main sequence star, luminosity, brightness. Brightness is how we measure it from Earth, right? Yeah. You understand what brightness is? So brightness is basically how bright it appears to us, right? So we're gonna use that to determine how far is it away from us. You get what I'm saying? Like what's the equation? What are the base equation? This one luminosity. No, so brightness is basically L over 4 pi d squared, right? Yeah, I mean if we know the exact value of brightness and we know the luminosity, exact value of luminosity, we can actually determine the distance. The problem is all these values here are all given in the term of the sun. Right? It's like super annoying. So I mean, what's the brightness of the sun, by the way? The brightness of the sun will be equals to to the luminosity of the sun divided by 4 pi, okay, AU squared. I think maybe you were missing this part. But do you understand why is it like that? What does AU stand for? What does the astronomical unit stand for? Data booklet. Data booklet. What does AU stand for? No. Yeah, I know the distance, but what does it stand for? Oh, it doesn't read. It's not written there. So you need to know what AU is. Yeah, that's right. So AU is the sun Earth distance. Yeah, the sun to Earth distance. So if we use the brightness of our sun, luminosity of the sun divided by 4 pi AU squared, that will be the values of the sun. And I think we need to use that to fit it into here to make D in terms of AU. I think that's what we're supposed to do. You get what I'm saying? Because for the theta 1 Orionis, B is 4 times 10 to the power minus 11, right? Brightness of the sun, solar brightness. And then this is equals to 4 times 10 to the power of 5 solar luminosity over 4 pi d squared. Then you're supposed to make D the subject in terms of AU. Can you do that? Yeah, that's the answer for that one there. Yeah. Yeah. Okay, we'll just yeah, there we go. Yeah, this is one. I think what happened to her is that she didn't realize that this solar distance is AU. Like this one here is AU here. Like I mean I would just present my working like that. It's the same working, but yeah. Okay, what's the next question? Ethan 10. All right, let's go with 10. 10, 10, 10, 10. Say what? What? Which one? What happened? What happened? Which one? Which one? Oh my god. This one. Ah. Oh, good. 2SF. Okay. Okay. Yeah. Average induced EMF. Final minus initial. Yeah, final minus initial. 6 cm to 12 cm. Let me see this. Oh, the just changed. Okay. Okay. Oh, yeah, it's just a change. Okay. Oh, that's gross. Oh, this is so gross. Okay. $10D double I. This one? Yeah, what's up? Huh? It's just it's oh my god, you wrote the correct working, punched it wrongly. Okay, but towards the end of the paper is usually the issue. Okay, what's this, man? Oh, deduce. Okay, so I guess this one will be a problem lah. Right, space-time question. Deduce using space-time diagram which light was turned on first according to observer P. Right, so P is in the train. Right, P is in the train, and then you're supposed to, right? For Q, both lights are instantaneous. So simultaneous to stationary observer does not mean simultaneous to moving observer, right? So you probably will have to draw lines like this and lines like this to determine. Wait, hang on. I think I'm doing it wrongly. Oh shoots! I need to figure this out myself. Oh yeah, no, yeah. You're supposed to figure out. Um, wait Oh yeah. Down here and down here like this. Yeah, different times. So this is as it's moving towards So yeah, it will this like lamp F will light up first, and then according to the time axis, lamp B will light up second. So F first, B second, then B second. Yeah, that will be this one here. Yeah, it's towards this way, right? Yeah. Okay. No, that was it. Okay, can. That's fine. Okay. Hey, any other things? Any other questions? You. Hmm. Not difficult. Mm. Not difficult. They're not trying to be fun. Mm, but you know what I'm looking at? I'm looking at a major part of all the things that I've covered before. Like the worst thing. I mean, to me, I say it's not difficult because I'm looking at all these things. Like for example, these 3 marks here. I've covered it all before, right? Like, oh my god, what? Why would you not do that? This one here will be maybe lack of practice because we usually don't do a lot of astrophysics questions. Um, this gas one, there ain't no way that you should be getting this wrong, right? And I went through this many times before as well. Nothing out of ordinary actually. This is easier than your CTs. Remember how I was getting them pissed off by your CTs? Yeah. No. CT was a lot more pissing off. No. So what was really difficult was your paper one. Remember the last 8 questions, the stupid paper one questions? Yeah. That was a pain in the ass. Sorry, 1B. Let me finish up with 1B. Anything else? Sorry, did anybody send me anything? No, okay. Yeah. 1B. Did anybody want to ask? Oh no. Oh no, missed out the first mark here. Goodness. Oh my god. Yeah, the gradient. So that's the thing, right? I've done this before too. Like the gradient of a I V oh no shit. Now VI graph, yeah. The gradient of this graph is, does anybody want the recording for this? No, that one is a I like Ohm's log IV graph. Okay. Hang on, let me just find the. Gosh, goodness. Wait, let me search for this thing magic first. Hang on. Alright, oh no, yeah, it's not during the holiday season. I'm trying to. This one right here. Okay, wait. share specific timing, right? Telegram, right? This one here, right? Do a screenshot for your context because this is to show you the graph. That's right there. And then, yeah, I mean, this way I really can cover a lot more things, right? Rather than you all just like sit there and then just listen to me repeat the whole thing over and over again. And then I want to screenshot this original question here, right? Which is this one here. Goodness. Anna was like, oh no, I just totally forgot to do the first question. It's quite funny actually. Okay, there we go. There you go. Okay. Um, what's wrong with this? Yeah. This, no lah, this is acceptable. The answer here is acceptable. Wow. Okay, wow. Right, for yeah. So it's a systematic area, but it doesn't change the gradient, and therefore the internal resistance calculated from the gradient is still the same. But you had to know that the internal resistance was the gradient in the first place, lah. Wow, that's impressive, man. I mean, the 1B is not easy. Yeah, the 1B is not easy. Mm-hmm. You know why? When you say R equals to V over I, you're basically finding a point on the graph and then finding the V and then divided by the I. That's wrong, man. Yeah. Oh, you did that? Did you actually find the gradient? Do you get this value? Oh, no. No, you have to go fight for it. And then you're absolutely correct. There's nothing wrong with that. Yeah, these people are weird, man. Inconsistent marking. How much did they minus off from you? Oh man, that's not worth it. No way! Oh my god, this thing came out. Damn. He lost the surroundings. It's a thing lah. I guess I gotta make sure that you guys get it. Um. He lost the surroundings. Yeah, it's in my. Whew, was it B1? Jeez, it's probably B1. Wow, the IB they really teach you damn broad things. Like seriously, like I have to cover so much content with you guys. Whoa. I have to cover so much content with you guys. Where the heck is it? Oh man, I forgot where is it already. B1 part 1, maybe I have to go to B1 final. Yeah, there we go. It was right about here. Why is my internet so slow? Yeah, there we go. So you have to learn how to eliminate heat loss of surroundings. Wow, it's a thing, man. Shit. I mean, yeah, I have to incorporate all this into my lessons. So we have, wait, I'm gonna send this one out as well. Not the year threes. Year five. Year five. General. And then I need to take screenshot here to help you understand this nonsense. Key losses surroundings. Hey, next week you all remember to come for class, next week. I want to buy some food for you all. Okay? Probably I mean I will make sure that you when like you know I'll take your head count, but I'll probably buy some pizza from the side. So just I mean just turn up lah. Wait oops. The question that I want to screenshot is this question here. Like why do we yeah, so it's this one here. To explain this part here. Okay, there we go. Right. Anything else? Oh, can I go through the zero error again? This one here? Oh, so the idea here is that since there's zero error, right? All the current values are either more than or less than, right? So the idea here is that even if you get all more than like a certain value, that means the entire graph is just shifted this way like this, right? But then it means that the gradient is not changed, right? And how do we find the internal resistance, Laura? The hello? Are you talking about this question? Yeah, right. Okay. So basically, right, if your ammeter has a zero error, all the readings, like you take a reading here, it will offset to the right side. You take a reading here, offset to the right side. You take a reading here, offset to the right side. You get what I'm saying? Yeah, but that means that it will be a consistent error, which will shift the entire graph to the right, and therefore that doesn't change the gradient at all. The gradient is still the same. Yes, the gradient remains the same, and therefore the internal resistance remain the same. Can anyone tell me what would it affect? What will having the systematic error of the ammeter affect? Like what reading would it affect? Like I'll buy you a donut if you can tell me that. If my systematic error causes my graph to shift this way, okay? What? Not donut level kind of answer, but you're not wrong, but it's just that what specifically? What? Nope. Come on, a donut writes on this, man. A box of donuts. Jeez. Yeah. Like if your ammeter has a systematic error, the internal resistance is not affected because the gradient is not affected, right? Something else is affected. Laura almost got the correct answer. She said voltage, but that's not quite the level of like answer that I would give a box of donuts for. What is the exact thing that okay? What other things can you find from this graph? Then everyone's scrambling to go and watch the video now. Yeah, Laura, I give you half a donut, okay? If you extrapolate this thing backwards and you cut the y-axis, that's the EMF of the cell. So having a systematic, a zero error ammeter, right, will cause you to read or cause you to have a wrong reading of the EMF. Like the true EMF would have been 1.5 volts, but then a zero error ammeter will give you the wrong EMF of the cell, right? When the current is zero, right, the reading of the voltmeter is the EMF of the cell. Catch that thing. This lesson here would be very clear on what I'm doing here, like this thing here. Catch it over here, like it's right there, right? You see, I even explained that this EMF is here. Okay, right? Yes. So please, yeah. I mean, that's it for the review. I'm done. Okay. Chaco and Ephraim, do you have anything else from SL paper? Okay, good. Thank you very much. Thanks all. Next week, please. What? Sorry. Oh, that I'm saying that I'm just saying that this answer is correct. Like I don't know why your teacher marked it down. I mean, if anything, right, a zero error is a systematic error that gives an error of a fixed value, right, of a specific value in a specific direction. I don't know why they underline fixed and then give a zero. I think the this one the teacher has a certain way. This is probably an A-level teacher, by the way, right? Only A-level teachers love to ask these kind of stupid questions. I mean, background, A-level background for IB papers. Okay, saying that it's a systematic error at the IB level is really good enough. Really, a zero error is a systematic error, right? It is understood that systematic errors are errors where it's of a specific value and a specific direction. And then when we say direction, okay, direction means that it's either a addition or subtraction of the actual value. So I don't understand why this answer is not acceptable. This answer to me is like perfectly fine. Okay. Sorry, what? It measures a value when there's no input given. I mean, that's kind of like a duh lah. I mean, wait, you're not wait. You said that and you got a mark. Uh huh. Uh huh. Oh, but you got a mark, right? Okay. Okay. Sorry, who's asking the question? I thought that was Laura. Mansa is talking now. Oh, 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 you are okay. Okay. I mean, there's no need to. It's understood that okay, a zero error is a systematic error that is an offset from the zero value. Oh my gosh. If that's the answer, I'm gonna kill them. because it's like, yeah, we know why can't we say this? This is perfectly fine. But okay, fine. A zero error, I guess if you want to really define it, it will be an offset of a value from the zero mark. When the system when the apparatus is not being used, when the instrument is not being used. Is that okay? Ken? Okay, yeah. Pizza next week, guys. Yoo-hoo. I have to do a head count. I have to make sure that you all can eat. Bye. Thank you. Bye bye. Thank you. Thank you.